Okay, Assalamualaikum semua students. So today we are going to continue the lecture for week 10. So the lecture today is going to be on a single component vaporizer. So you should be able to find all the information from your textbook of page 51 and subsection of 3.7. So in this case we are going to discuss on the single component vaporizer. So one of the important features here is that this is actually a boiling system, and from the textbook you can actually read that this is one of the most interesting and important operations, because and also it is among the most difficult to model, because of course it involves the evaporation part. So this system usually is very rigorous, and to do the balance you have to write the equations TCE, the CCE and energy balance for both vapor and liquid systems, but of course it is all depending on the assumptions that you use to write the equation. So, and also the problems that you have to determine in this case, the most difficult part is determine the rate of vaporization of material from liquid phase to vapor. From the example in the textbook in figure 3.6, we are going to use liquefied petroleum gas LPG, and in which the LPG is fed into a pressurized tank, and you are going to hold the liquid level in the tank, meaning that we are going to have a constant H. Okay, the liquid level of the tank. Then in here we will assume that the LPG consists only a pure component, that is propane. Okay, and in here we are going to assume that the liquid tank is perfectly mixed, meaning that in here you can going to have the density, there's the density of the liquid, but of course the density of liquid and the density of vapor, they are not the same thing. Okay, heat is added at the rate of Q to hold the desired pressure in the tank, and once you have your Q, means that you can actually control your WV. WV is the rate of the liquid vaporizing from liquid to the vapor phase, and the unit is mass per time, and also there is no heat loss to the surrounding. So gas is drawn off the top of the tank at the volumetric flow rate of FV, and FV is a forcing function or load disturbance. So for this system we are going to use three types of assumptions. The first one is liquid in the tank is perfectly mixed. So you know what it means. It means that the density in here is uniform throughout the whole system. And number two, the pressure in the tank, okay, noted by P, is controlled by the Q supplied to the tank, and thus it controls the rate of evaporation of the liquid to the vapor. So please note that the unit for WV used here is kilogram per time. And the third one, this is for energy balance. The heat losses to the environment is negligible. Okay, means that we assume Q from here, from the liquid from the tank, is equals to 0. So all Q used here, all Q supplied to evaporate the liquid to the vapor phase. Okay, next one. So in this for this particular case, we are going to discuss four types of model. The first one is steady state model. Number two, liquid phase dynamic model. Number three, liquid and vapor dynamic model, means that we are going to consider both of it. And number four, it's a thermal equilibrium model. Okay, so this is particularly for energy balance. And of course all this you can actually use of all these type of models depending the assumptions that you take for every particular system. Okay, the first one, the steady state model. Okay, so we have to use the assumption that the pressure of the tank is controlled by the Q supplied to the tank, and thus it controls the WV. So for this particular case, we are going to omit the fact that our d over dt is equals to 0. So we are going to develop a very simple equation, which is Q is actually equals to WV, okay, times the enthalpy of vaporization minus the enthalpy of liquid system. And since your WV is equals to FV rho V, your WV cannot be measured directly. There's no device you can use to actually measure the WV directly, but we know for the fact that your WV is equals to this equation, and you can actually measure your FV, and you can actually calculate the density of vapor, which is depending on the equation of state that you use. Okay, example of equation of state: PV is equals to MRT, which is depending on the pressure. Okay, so thus we can always replace WV is equals to FV rho V times HV minus H0. So this is your first equation for steady state model. Okay, the next one is liquid phase dynamic model. So this is valid if we assume that the volume of the vapor phase is small. Okay, or this is also valid if we assume that the dynamic of the vapor is very fast going out from the system. Means to say that you cannot actually able to capture the change of volume of the vapor phase with time, because it happens very fast. So for this type of assumption, then it makes the assumption you are only need to develop the model for liquid phase only based on this assumption. So in this case, if only few molecules is needed to change the pressure in the vapor phase, okay, then the pressure of the vapor phase is equals to the vapor pressure of the liquid phase. And thus, once you make this assumption, then you can, in order for you to calculate the pressure of the liquid phase, you can use the Antoine's equation. Okay, remember this. Next, okay, so from here we can actually develop the TCE for the system, and remember the TCE is only for the liquid phase. And let's do this. D rho VL on dt equals to rho naught F naught minus rho V FV. Okay, excuse my pen. And this one is actually equals to your WV. So you can use either WV or rho VFV. Does not really matter. Then for energy balance, so we're going to go straight to the final energy balance, because you already know how to actually develop it from the basic for energy balance. Make sure you know how to do that. So it's CP rho d VLT on dt. Okay, this one looks familiar. It's the same, is equals to rho naught CP naught F naught D naught, oh sorry, minus rho FV CP TV plus, oh dear, lambda V. Please don't forget that. Oh dear. Plus Q. Okay, so please write down your general equation. Okay, then Do you remember that you have to determine the density? Then you can actually use, since ideal gas is assumed in this case, then the perfect gas law is used, then you can use PV is equals to nRT. So your density of vapor is equals to M, oh goodness, P over RT. And the Anton's equation, remember you have to find the vapor pressure of the liquid. Epsilon P is equals to A on T plus B. Everything is in your textbook. So when you have this, means that equations 3.35, which is originating from your Q, is equals to a function of pressure. Okay, so this one is the feedback control relationship. One is F naught is equals to, as a function of volume. So of course this is the feed here, and you see you have a level control there. So of course it's depending on the volume or the height. From the height you can actually calculate the volume. So, and the Q here is actually as a function of the total pressure, okay, of the system. And it's not a problem because we are assuming that the pressure of the liquid is the same as the pressure of the vapor. Okay, the next one, oh yeah, okay. So from here, from all these equations, if you calculate from equation 3.35 to 3.39, you should have 6 equations. And once you have 6 equations and also you have 6 unknowns, then it can be solved. The unknowns in this case is Q. Okay, you don't know how much you have to give Q to make the pressure stabilize. Then your F naught, okay, and your pressure VL, rho V, your T. Alright. Okay, next, let's continue to liquid and vapor dynamic models. So in this case, so if the dynamic of vapor phase cannot be neglected, meaning to say that if you have a large volume of vapor, then your total quantity TCE and energy balance must be written for the gas phase as well. Then the vapor leaving the tank is not the same as WV dynamically, means that it does not happen at the same time. Okay, so the problem here is that to find what is WV. So in this case, we are going to use the relationship of WV is equals to KMT times pressure P minus PV. So your P here is actually the vapor pressure of the liquid, and your PV here is the pressure of the vapor. So what happened now is that, okay, the driving force for the liquid to evaporate is depending on the change of pressure between of the liquid and the change of pressure of the vapor Okay, so let's put down here the driving force, yeah, for evaporation. Okay, so your KMT is actually it's a pseudo mass transfer coefficient, and at equilibrium your pressure is equals to PV. So your P here is actually PL. From the beginning of this lecture, I use PL as a PV. Already excuse my pen. So at equilibrium, our pressure in the liquid is the same as PV, is equals to PV. Then in this case, when your PL is equals to PV, then your WV is equals to KMT. Okay, this is from this equation here. And the liquid will boil when the vapor pressure in the liquid is very, very large compared to the pressure of the vapor. Okay, so next, from that we can actually do some derivation of both the liquid phase and your vapor phase. So let's do for the dynamic model for liquid phase first. So for TCE for liquid phase, then we know it is rho dVL on dt is equals to rho naught F naught minus WV. Okay, it's only for liquid phase. Then the energy balance, it's rho dVL U over dt. Later you can change this one to H, then to CPT, equals to rho naught F naught H naught minus WV H L. Okay, so at this stage, plus Q. Okay, please note that we use HL because this is a pseudo phase between liquid and vapor. And we have a vapor pressure equation. So this is actually from your Antoine's equation, just like before. Okay, P is equals to E A over T plus B, or ln P is equals to A over T plus B. Okay, now let's do the balance for vapor phase. It's d on dt of VV rho V equals to WV minus rho V FV. It does make sense? Yeah? Okay. The energy balance, d VV rho V UV on dt equals to WV HL minus rho V FV HV. Then the next one is equation of state. It's rho V is equals to M PV over R TV. So in this case, we assume ideal gas equation, pressure less than 10 bar, or pressure less than 2.5 bar. It depends on your school of thought. So in this case, we have 9 equations but 10 variables to determine. So the 10 variables, the unknowns are Q, F naught, VL, everything is rigorous. WV, T, VV, rho V, TV, and rho V. Oh, sorry, PV. It's PV. Okay. So in this case, from equations 3.35, just now was equations for the control, okay, level control and the pressure control, and to equation 3.49. Equation 3.49 is until the equation of state that we use, that is ideal case equation. So you only have 9 equations. So please check your textbook. Something is missing. The textbook said something is missing, meaning that you have to find one more equations that makes these equations able to be solved. So in this case, a very simple one, the total volume of the tank. Total volume of tank equals to VL plus VV. A very simple equation. So once you have this, you have 10 equations, you have 10 variables, meaning to see that you can actually solve the equations. You can solve the parameters. Okay, the next one, thermal equilibrium model. So in this thermal equilibrium model, what happened is that we are going to assume that the temperature of the liquid and temperature of the vapor is the same at all the time. So in order to make our energy balance is easier, so we can, from that we are assuming that the temperature of the liquid and the temperature of the vapor is the same because they are in equilibrium. Just in the case, then from here the energy balance of vapor phase is not needed. So we only have to focus into only one energy balance. It makes things simpler. Then the energy balance for this equation is, okay, so if in the exam you have to actually derive them from the beginning, but in here because you already know what is expected, so please write down your general equation as well. So in here what happened is that you can write rho Cp d VL T on dt is equals to F naught rho naught Cp naught, okay, T naught minus WV Cp naught T plus lambda V plus Q, and the whole thing here is actually equals to your HL. Okay, and this one refers to your H naught. Okay, so that is the end of